So based on like what circuit we had discussed, like which is on the right side, we will start discussing on uh, program, actual program. So in the last class, we have seen that how we actually like we have to make RS, EN, and D7 to D4, how to use that, and like how that VE contrast work, right? So first, like you can just remind me, like what do you mean by RS?
Sir, I couldn't hear you properly. What was the question?
Is it
Sir,
audible
RS
now?
is for a register subset.
Register select, right? So it is going to select whether like I'm giving the command or it's a data, right? And we have enable. What do you mean by that? What that mean does? So from high to low transition distance will latch the data into LCD. And we have 4-bit data. What is the use of that 4-bit data? So we are sending
Sir,
the
it's
actual
a
data.
special case.
Yes, it's a special case. Actually, it should be 8-bit data, but we are using only 4-bit data. That is one of the mode. Right? So by setting that command, by sending particular command, we are setting that into 4-bit mode, LCD mode. So on that end, we have seen. So if you see the header files, so coming to this part like LPC2148.h, which is like LPC214, since we are interfacing with LPC2148 device, we have to call this header file. And here, like I'm setting like what is the PLL setting, plog. That is actually the status of LPC2148, which will tell me whether I have logged into particular clock. Clock is setting. And apart from that, like we have LED on off. That is anyway like it's not scope of our discussion because like right now we are not bothered about LEDs. So basically we are bothered about these pins, RS on and enable on. So if you see RS is connected to port 0 to 20th pin, right? So that's where you can see I'm shifting one left shift by 20. Whenever I'm saying I want to make RS on, I want to set it. That is, I'll setting like port 0th pin, I'm setting to high whenever I call this RS on. Whenever I call RS off, then I am clearing 20th pin because I have connected this RS to 20th. And whenever I want to make enable high, I'm setting 25th bit. Left shift is nothing but it is going to make the 25th bit as high, right? So set is something like whenever you want to make that register, make that port as high. Clear is actually whenever you want to clear that, make that pin low. So enable off will clear that pin, right? And we have various functions like system minute, millisecond. So this is the function declaration because like later we have the function definition of detailed definition of that like architecture of that. But here it is like just we are declaring those functions: send data signal, send higher nibble, command write, data write, read higher 90. And coming to main function, first we call this system init. So as we seen, like basically in the system init research, so you can see we are configuring the PLLs, right?
Yes, sir.
So we are setting all the clocks basically. We will set all the clock frequencies. I think like in UART also we discussed like this PLL con, PLL config, PLL feed, PLL feed. So basically we will set the frequency of the clock, and we will try that PLL gets locked. So as we have seen the PLL lock, right? So here you can see PLL0 status. We'll read the status of the PLL0 and we will check whether that is locked. So if that is locked, then I will set that like PLL lock register and I'll come back. So this is system initialization which will be common for all the programs. And depends on like what frequency you want to operate to interface. Okay, but actual scope of discussion today is like on the LCD end, how we are interpreting. So you assume that like all our clock initializations are done, that is system initialization is done. Next, basically, we are sending actually in which port P0 to P16, right? P16 to P23. I mean, out of that, like we are actually using, yeah, some pins are not used. So I'm making that as output. And in first pin, right? First pin, what I'm doing, I'm actually setting 25th bit as output, because like in the first pin I'm using enable, first port I'm using enable, and 0th port I'm using actually for data and read select, right? Read or register select. Then you can see LED on, that is just to see actually LED on is something like it's just for showing the status that you have initialized successfully and you are starting LCD. But this statement is like need not be always there. I mean, it depends on you whether you want LED to glow or some status you want to display. If you don't want to display, then this can be skipped, and then you have to reset the LCD. So coming to LCD reset function. So basically, we are sending this is actually sequence of bytes what we have to send for resetting the LCD. First, we need to send higher nibble as 30, and then we will send again, like after 100 milliseconds, we will send 30, and then 30, then after some time, we send actually 20. Okay, so post that, so here actually see, you first we are actually setting the higher nibbles, and then we are saying whether it is a command or data. So here all are actually commands. And if you see this function also, send nibble is something like we are actually sending the data at 16 to 19 pins, that whatever the data is there, we will set in that. And whenever this command signal, send command signal is called, I'm making enable high to low transition. That's what the data should be, right? So first actually, what I have to do, I have to send that 4 bits. I have to keep that in pins. Like if I want to send 1010, I'll keep that data in these pins, 4-bit pins, and then I will make that enable from high to low. When I will make this transition, then all the data, whichever is present in those pins, that is going from pins to actual LCD register. Okay. So first, actually, I am resetting all the LCD. Resetting in the sense I bring all the registers into default state and I'll clear all the LCD. Then I have to initialize the LCD. If you come to the LCD initialization function, I'm sending 28. So if you have seen like previously in the previous class we discussed, right? 28 is something like it's a 4-bit LCD mode, correct? And I'm saying it's a 5x7 LCD matrix type. It is nothing but here you have seen setting the functional register, right? So it is here function register. So DL I am making 0 so that it will be 4-bit mode, and this N I'll make it 0, and like F I'm making it 0. That is like 5x7 dot matrix. So that's where I have to keep it at 28 so that my LCD will be in 4-bit mode. Okay. Then I will send E, that means display on, cursor on. I mean, you can just refer the table what we discussed last class. And here ADU, that is actually we have to go to the first line, first position. That is a command. Okay.
Yes, sir.
So we will start now. I mean, the command came to the initial position and the displaying will start. So you can see here, this character got displayed, right? LCD display string, RE College of Engineering, 4th Computer Science. For this way, actually, whatever the character you want to display, you will just put it into that display string. So, and see, actually, we are saying this like 80C094D4. That is actually 4 lines. The command read 80 for the first line, C0 for the second, 94 for the third, D4 for the fourth. It's actually if you want to display on the 4-line LCD, right? We'll be going through that sequence of command. Then coming to this LCD display function, right? You can see we are fetching that character, whatever you send, right? So we are like fetching one by one, character by character, and then we are calling LCD data write. So in the LCD data write function, so whatever the byte is there, that like I'm splitting into like that 8-bit data and splitting into 4 bits, higher equal lower bit equal, and those values, right, byte by byte, nibble by nibble, and push into the 4 lines, whatever is connected, right? So it will be pushed into 4 lines. So you can see here P16 to P0.16 to P0.19, and we will be making it enable by below. So that data will be displaying on the LCD. Okay.
Yes, sir.
Any questions here?
No, sir.
Hope you got the flow how it happened.
Yes, sir. I got an idea.
You want me to elaborate on it?
Sir, I couldn't hear you.
If you want me to explain any section of the code in more detail, you can, we can discuss that as well.
No, sir.
Is this fine?
Yes, sir.
Oh, oh. And shall we move to the next
Yes, sir.
interface?
So, which is the next interface?
ADC.
How?
Analog to digital converter. So, what do you mean by ADC?
So,
So,
analog to digital.
yes, which converts analog signal, which is continuous in time, to digital signal, like ones and zeros, right? So, especially this ADC, right, in case of our microcontroller embedded system, it finds application in interfacing, temperature controller, temperature measurement, right? Speed measurement, like you have seen speed, uh, like speed measurement in your automobiles, right? So that measurements, stress measurement, strain measurement, humidity measurement, rain sensors, LDRs. So many applications. So ADC is one of the most important interface in our embedded systems, right? So like there are various types of ADCs also. One type of ADC is dual slope ADC, and second type is successive approximation method. Okay. So coming to the architecture of ADC, like how typically it will be interfaced, right? We'll see this kind of interface, like where you will feed this voltage to the input of the ADC. Then you will actually get digital outputs. So it can be parallel also, like 8-bit directly will get 8 bits, 16-bit or 12-bit. That is a parallel interface. Or you can also read this data using serial interfaces like SPI, I2C, right, etc. So here you can see two signals like SOC and EOC. That means it is a start of conversion and end of conversion. So these are the signal which we require to control, like where to start our conversion of analog to digital and like when to end. Okay.
Yes, sir.
So coming to, there are like some important factors what we need to understand in the ADC. So one factor is like, for example, if I have 8-bit ADC. So in 8-bit ADC, what is the minimum value I can represent? I have 8 bits of data. In the 8 bits of data, what is the minimum value I can represent using that 8-bit?
Sir, I didn't get your question.
My ADC is 8-bit. Okay, I have 8 bits. I can use 8 bits. Okay, 8 bits. Like for example, I can give you example. Like I can use 2 bits. If I say I can use 2 bits, I can like have like 0 0 is the minimum value and 1 1 is the maximum value. 1 1, when I say 1 1, it's like 3 is the maximum value which I can represent using 2 bits. Now I have 8 bits in ADC. What is the minimum value I can represent?
So 4 bits.
No, it's 8-bit ADC, so 0 0 0 0 0 0, right? So this is the minimum value, that is 0 I can represent. What is the maximum value I can represent? That is F. That is all are ones, right?
Yes, sir.
Yeah. So here, when I say 8-bit ADC, the 0 corresponds to minimum voltage, 0 volt. And FF, what I get, the 256 is the maximum voltage. Okay, so this 0 to 256, like okay, 0, and like for 5 volts I get 256. So basically 0 to 255, that they are divided into 255 different parts, right? So whatever the voltage is there, V, I have to divide by 255. This is the minimum voltage resolution what I can have in my ADC. If so this V is 5 volt, 5 by 255, what is the value? Almost 20 millivolts is the minimum resolution. So in a sense, if I get 0, that means 0 volt. If I get 1 as a number, then it is 20 millivolt. If I get 2 from ADC in binary, it means 20 millivolt plus 20 millivolt, 40 millivolts. If I get 3, it means 60 millivolt, so on. If I get 256, or 255, then it is actually 5 volts, right? Correspond to 5 volts. This way we have to map whatever the digital values we get, right? We have to interpret in terms of voltages. Clear? Did you get the point?
Yes, sir. Yes, sir.
Yeah. So whatever I discussed so far, that was actually with respect to generic ADC. So any ADC, that is the case. But coming to specific to our LPC2148, coming to specific of the LPC2148. So basically LPC2148 has two ADC channels. Two ADC channels. That is ADC 0 and ADC 1. Okay. ADC 0 provides 6 analog inputs and ADC 1 has 8 analog inputs. Okay. And these ADCs are 10-bit approximative ADCs. When I say 10-bit approximative ADCs, so previously when it is 8-bit, I shown you some examples. So here, what is the minimum value and maximum value? 10 bits.
So it's the same, so like the minimum value is 0 and maximum is FF.
No, it is a 10-bit, right? So it is FF, and you have this also 3FF, correct? Because 2-bit, again 2 more bit will add. So FF is only 8-bit. Now we have 2 more bits. It is 3FF, correct?
Yes, sir.
Now if you want to find the resolution, it is actually 5 volt by 3FF. You have to find, this is the one count value. If I get 1, what is the value is 5 volt by 3FF. If I get count as 2, then it is 2 into 5 by 3FF. Finally, if you get maximum count, that is 3FF, that means it is 5 volts, because 3FF into 5 by 3FF, it is nothing but your 5 volts. Hope you got an idea.
Yes, sir.
So the sampling rate, that is like how much maximum samples it can have, is actually 4000 or like 40 samples per 40 or 400 kilo samples per second. This is the maximum speed what it can. Okay. So now we have various registers corresponding to ADC. We will see one by one. First register is ADC R. That is ADC control register. Okay. So this basically used to select the operating mode. Operating mode of the ADC. Okay, ADCR. And we have ADC DR, ADGDR. So it is actually global data register, which used to once ADC conversion is done, right? The result is stored in this. And we have one more register called AD stack. So this is actually ADC status register. Okay, so this register contains, like, once the ADC is done. Okay, so you can see that status here in ADC stack. And same way we have ADG, DR we have seen, SR. That means that is also status register. So here also it contains like all the, whether it is done, all these things. Okay, the ADC done, overrun flag, all this. And we have another register ADINT enable. That is ADC interrupt enable. So whenever this ADC is done, I mean, like, if you write simple program to keep in a while loop, keep polling whether ADC is done or not, then the issue is, like, you may not be able to know when it is done. I mean, you will keep polling that point itself, right? So that's where, like, you can use ADC interrupt enable. If you enable the interrupt, you can perform the normal, keep performing the normal operation. But whenever the ADC conversion is done, one interrupt will be generated. So you can just come here and read that. Okay.
Yes, sir.
And finally, we have ADDRX. So ADDRX basically contains the most recent conversion. Okay. So I just put the block diagram of this ADC. So you can see, like, we have various channels. So we have to select which channel we want to read, and, like, you can see the status register, global data register, and all the data registers, and interrupt enable rule. So whenever you receive the converted data, so it will get in that ADC and you can push into various data registers. Okay.
Yes, sir.
So next we will see what are the steps to program this ADC. Okay, today we will see these steps. Then next class I will discuss the program. Okay. So the first step, I see here we have various pins. So we have to choose which pin is suitable for us using pin select register. Pin select register, we have to say which pin I want to choose as an ADC. So then next, actually, I have to write the ADC control bit. Using the ADC control bit, right? I have to say what are the configurations I want to make. So, like, first I have to in the ADC control register, 21st bit, I have to say use the ADC, switch on the ADC. Then in that, I have to select the channel. Like, we have bit 0 to 7. In that, I have to say, here you can see that 0 to 7. In that, I have to say which channel I want to use. So pin select is, it is corresponds to pin. Like, we have various ports. That which pin we want to choose as an ADC pin. And then within the ADC, which channel you want to choose. You will be saying. Then you will say start of conversion. you'll say like start of conversion. That is actually you will be writing 001 to bit 26, 25 and 24. Okay. Then in the GDR register, you will check whether conversion is done. Okay. Like 31st bit of global data register, you will see whether ADC conversion is done. So if that conversion is done, then from the GDR register itself, you will read the 12 bit. Okay, from the same register, you will read the 12 bit. That is nothing but our converted data. Clear?
Yes, sir.
Any questions so far?
Oh, no, sir.
Maybe one quick program also I can take.
Yes, sir.
So this is actually light intensity diode, how to interface LDR, light intensity diode. So if you have seen in your automobiles, nowadays like automatically as soon as you enter, I mean whenever it is dark or like as soon as you enter any tunnel, when there is like low lights, automatically your headlights will turn on. So that is like basic function of your LDRs. And like now street lights also is like enabled with LDR. So the circuit for that LDR it will be this. You can see through one op amp, it's a voltage follower just to match the impedance. The LDR is there. So this voltage is coming to your AD1.3. This way we interface. So that's where like here this LED on, LED off just for the status purpose. So P0.21 I have made it as output and P0.28 I'm using for reading. So that P0.28 I'm setting as high, the 24th bit I'm setting as high to make that as a ADC in. Okay. Then I'm saying ADC control by like a reading purpose actually. Okay. I'll read that. So then I will say that check, see actually if you see the steps, right? The ADC control bit, I'll actually like say ADC here, I'm making like bit 0, 7 and SOC, I'm saying start of control, I'm like making high, right? So that is this operation. The step 2 what I mentioned. And step 3 what I mentioned is this operation. So I'll be keep reading this ADC zeros, 0th first bit, the MSB bit to see that whether the ADC data is ready. If the ADC data ready, right? So then I will check the data, that 3FF, I'll read the data, that is step 3. So then if that is greater than 100, it means if that actually there is no light is falling on, a light is falling on, then LED will be off. Okay, if the light is falling on, so the resistance will be low and analog value will be high. So as the resistance decreases, your voltage level increases, right? So you'll have more than 100, then you have to switch off the LED. So if it is less than 100, then what we have to do? We have to switch on the LED, right? So it is like just comparison of resistance. So if the resistance is, whenever light is falling, resistance will also fall, right? When the resistance is falling, your voltage will increase. So you can see that's why like greater than 100, it will become greater than 100. So when it becomes greater than 100, it is indication that some light is falling on the light detection resistor. But when that actually finished, okay, I mean whenever the light is not falling, then what you have to do? You have to actually, I mean the resistance will increase. When the resistance increases, voltage will fall. So when there is a voltage fall, then it means you have to switch on the LED. So it's like just switching on or switching off using LDR technique. Clear?
Yes, sir.
Any question here?
No, sir. So, I'll be performing this experiment tomorrow, actually.
Okay. Got an idea, right?
Yes, sir. It helped.
LDR is just a resistor kind of thing. If you close your hand on that resistor, then suddenly the resistance increases. So when resistance increases, voltage division. So voltage also decreases. When resistance increases, voltage decreases. It means actually you have to switch on the LED.
Yes, sir.
Oh, any questions? Any doubts so far?
No, sir.
Okay. If you are like not clear any concept, you can ping me also. Not an issue. Okay, please go through
Sir,
that.
after performing the experiment tomorrow, I'll get to know where I have doubt.
Sure. And LCD, have you performed that LCD experiment?
Yes, sir. We're done. I got the output too.
Okay. So that on that end you are clear, right?
Yes, sir.
Okay. Great. Okay then. We will meet tomorrow then. Tomorrow or like I'll let you know when is the next class. Okay.
Okay, sir.
Okay. Thank you.
Thank you, sir.
And also you can actually whenever you have doubts, right, you can just revise using the recording links what I showed. Okay.
Yes, sir. I was watching them.
Okay. Sure. Thanks.
Thank you, sir.